Okay. Find a time-based parameterization for a revolute joint of a manipulator. So a single joint, let's call it theta. The joint should move from 0 to 0.5 radians from time t equals 0 to time t equals 1 second. Okay, so what it's saying here is for the thing in red, theta at time t equals 0 should be 0. So t equals 0 should be 0. Theta t equals 1 second, it should be 0.5. Followed by movement from 0.5 to 1 in from 1 to 3, which means that when theta equals 3, time equals 3, theta should be equal to 1 radian. Okay, so that's not it. Here we have more conditions. Also, the velocity of the joint at the start of the motion and end of the motion should be 0, which means that theta dot at t equals 0 should be 0. Theta dot at t equals 3 should be 0. And then this additional condition looks a little strange. So velocity of the joint at the intermediate point t equals 1 should be 0.2. Okay, so what does intermediate point mean? Well, it's basically this one. So theta dot at t equals 1 should be 0.2. Okay, so those are the conditions. Now you could do it in one of two ways. One way is t equals 0, t equals 3, and there's 1. So what you could do is you could say I'm going to create a polynomial which basically shows the required behavior from 0 to 1, so 0 to 3, and I have 6 conditions, and I need to create a polynomial which would be, to satisfy the 6 conditions, would be fifth order. So a0 plus a1t plus a2t square plus so that's one way of doing or solving the problem. However, if you go to the last statement I made here, that just says that you cannot do this. You shouldn't. This is not what is asked. Don't take one single polynomial, but use 2 minimal order polynomials. What I mean by that is, instead of correcting 0 to 3 by one polynomial, you want to do something like this. This should be one polynomial, and then there should be another polynomial. So we can call this theta 1, this is theta 2, and they are valid on their own domains, but in general, they would basically explain theta as a function of time such that it satisfies those 6 conditions. Okay, so this is, as I said, not asked in this fashion, but you could totally do this. 6 conditions, 5 fifth order polynomial. But let's see how to do it by this constraint, which I just said. So you need to impose conditions on theta 1 and impose conditions on theta 2. So for theta 1 at t equals 0 is 0. Theta 1 at t equals 1, going by this, should be 0.5. Okay, now this one is not valid for theta 1 because theta 1 technically goes only from 0 to 1. So I'm not going to put anything which is beyond t equals 1 for theta 2, or so for theta 1, sorry. So this is 0.5. Then we have theta dot t0 is 0. So theta dot 1 at t equals 0 is 0. That's this condition. And then there's another condition here, which is true for theta 1. Okay, this is because theta 1 is between 0 and 1. So only theta 1 has domain of 0 to 1. So only those 4 conditions are valid. So next go to theta 2. Theta 2. So you will not have anything which will be at 0 because that's not the domain of theta 2. It only starts at 1, ends at 3, right? So theta 2 at time t equals 1. Clearly this should be true. So this should be 0.5. Then we have theta 2 at t equals 3, which is this condition, should be 1. Then we don't have this one. We have this one because it's at it's beyond 1. So theta dot t equals 3 equals 0. And then there's another condition here at t equals 1. That's theta dot t equals 1 equals 0.2. So theta dot 2 at t equals is 0.2. So those are for theta 1. These are for theta 2. Here the time is from 1 to 3. Yes, I think I've covered all of the conditions. So you see that what was supposed to be 6 conditions with a single polynomial is now going to be 4 conditions for theta 1 and 4 conditions for theta 2. So if there are 4 conditions for theta 1, what we'll do is we'll assume a third order polynomial for theta 1 and a third order polynomial for theta 2 because there are 4 conditions for each of those. Yes, so we just take that in just a matter of plugging in those 8 conditions. So let's take for theta 1 a third order polynomial. So theta 1 of t is a1 0 plus a11 t plus a12 t squared plus a13 t cube, where t is clearly between 0 and 1 because theta 1 does not extend beyond 1 second. And for theta 2, we have a20 plus a21 t plus a22 t squared plus a23 t cube, where t goes from 1 to 3. Okay. You also see that from the previous page that we will impose some conditions on the rate of change of position or the velocity. So we better get the velocity. So velocity theta 1 dot of t is a11 plus 2a12 t plus 3a13 t squared. And theta 2 dot equals a21 plus a22t, sorry, twice a22t plus 3 times a23 t squared. Again, the same condition holds. Okay, so now we are all set to go ahead and substitute the values of for these 4 conditions, and those will give us 4 equations for the first for theta 1, 4 equations for theta 2. So let's do that. So theta 1 t of 0, just put t equals 0. So we have a10 plus, that's it, a10 equals 0. So that I got from the first equation. Next, I have theta1 t equals 1 is 0.5. So I put t equals 1. A10, so t equals 1. That was 1. Sorry, my bad. It was 0.5, I think, 0.5. Next, theta1 dot at t equals 0. So I need to put t equals 0 in this expression. So I get a11 equals 0. Start velocity is 0. Theta1 dot at t equals 1. So I put t equals 1 here. A11 plus twice a12 plus 3 times a13 equals, it is 0.2. Okay, 4 more conditions left. Those are for theta2. So these 4 have to be met. So let's do that. Okay, let's start with theta2 at t equals 1. At t equals 1, it should be the same value as 0.5. So I put t equals 1, a20 plus a21 plus a22 plus a23 equals 0.5. Theta2 at t equals 3. I'm kind of forgetting what that is. So if you go here, you see that theta2 at t equals 3 is 1. So I put t equals 3 here. A20 plus 3 times a21 plus 9 times a22 plus 27 times a23 equals, let's see, it's 1. Okay, now I have 2 more conditions on the velocity. One is that the velocity at the end is 0. So that would be theta2 dot at t equals 3 is, we'll just take this expression, put t equals 3. So we have a21 plus 3 times a22, sorry, 6 times a22, because t is 3, so 3 times 2 is 6, plus 3 square, 9 times 27, a23 equals 0, and velocity 0. And then we know that the velocity at the intermediate point should be, I put t equals 1 here, a21 plus twice a22 plus 3 times a23 should be 0.2. So those are 8 equations, 8 unknowns. Yeah, so if it's 8 equations, 8 unknowns, if you can set it up as a, they are actually linear equations. So you can just set it up as ax equals b and solve for the unknowns, where x would be the a's. So I'll set up that matrix next. Okay, so the unknowns for this would be the a's. So a10, a11, a12, a13, a20, a21, a22, a23. And this is how you do this, populate this matrix. You can see that the right hand side is 0 and the left side has a10 equals 0. So first one, we need to fit in this one, a1. Okay, so what will happen is there's a 1 in front of a10, so you'll just put a 1 here. So then that 1 is multiplied with a10, you should get a 0. Everything else here is 0. there are 7 zeros except for that one single entry. So that's the first equation. The second equation you can see is this one. So I'll write it down first. A11 plus A12 plus A13 plus, sorry, I think it's A10 plus equals 0.5. Yeah, so what you see is there's a 1 in front of A10, 11, 12, 113. So 1, 1, 1, 1 for the first three unknowns, and then there's all zeros. That should be equal to 0.5. Okay, I'll do one more and then I will just write it from my notes. Next we have, let's skip this one. This is very easy. This as well. Let me do two more then. So A11 equals 0. So that will be A11 is the second element. So 0, 1. Okay. The third one is this one. So let's write that down. That will be A11 plus twice A12 plus 3 times A13 plus, I'm doing a mistake here. Is that right? I think it's right. No, there's no A10, okay. 2, 3, 1, 2, 3, 0.2. 1, 2, 3, 0.2. Okay. So this one has 1 in front of A11, and you can see A11 is the second element, so it'd be 0, or you can also write it like this if you think that's easier. 0 times A10. So 0 will be the first element. Then we'll have 1 for the second one, 2 for the third one, 3 for the 3 for the fourth one, and then since there are no constants or no coefficients with related respect to A2, 0, 2, 1, so on, there'll be 0. Okay, so then that I forgot to put 0.2. So that completes the first four rows. Now you could do that for the remaining 4 rows. You get something like this: 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 3, 9, 27, 0, 0, 0, 0, 0, 1, 6, 27, and 0, 0, 0, 0, 0, 1, 2, 3. What you have here is 0.5, 1, 0, 0.2. Okay, so what we have is, let's call this matrix as the capital A. Let's call this matrix as B, and let's call this vector matrix, the way you like to call it, as small a. So we have A times small a equals B. So A equals uppercase A inverse times B. So clearly an 8 by 8 matrix, you don't want to do this by hand. Although this particular matrix, it may not be that hard to get the inverse because there are lots of zeros in that matrix. But I used using Python, I got the values of A. So A is 0, 0, 1.3, minus 0.8, 0.55, minus 0.375, 0.4, minus 0.075. That would be A10, A11, A12, A13, A20, A21, A22, A23. Okay, so once we've got the coefficients, we've pretty much got the curve because theta1 is a function of, so theta1, remember, is A10 plus A11t plus A12t squared plus a13t cube, and theta 2 of t is a20 plus a21t plus 22t square plus a23t cube. So we've got a's, and we've got basically the function of time. Okay, so what does this look like? What I did was I wrote a code which takes this A matrix, the uppercase A, and lowercase b, and computes lowercase a, which is the unknowns. And then once it has that, you can then put it in theta 1 and theta 2 and basically look at what that trajectory would look like. Okay, so that's next. Python code. Okay, so this is the A matrix I just showed you, the one which came from our derivation. That's the B matrix. This is a function which is used to get the inverse of A, and there are many ways to get the inverse. Okay, so that's another way to do it. I think I've done it using the Skippy linalg before, but this is using I'm guessing it's just using the tools within Python. It doesn't require NumPy for that. Okay, then A10, A20, all that is basically the various values of x. Here, x is A in my notes. Once I do that, q, instead of writing theta, I wrote q, but that's the third order polynomial for q1, q2. I compute the velocity by taking the derivative of the position, which is done by hand, of course. And then the q1 double dot is basically the second derivative of q. Oh, cannot see the screen. That's interesting. Yeah, sometimes it seems like there's a glitch. When I share my screen, the notes are seen, but not this. Now, can you see the screen now? What I am showing you here is code which does some plots based on what I showed you in the notes. A matrix is this exactly copy pasted from my notes. B is again copy pasted. Here is a way of computing x. You take the inverse of A and multiply it with B. This you can see is slightly different from what we've used in the past. In the past, I think I used the Skippy package, but here I'm just using the regular tools in Python, not particular package to compute the inverse. Here is the various constants from x. Then what I do is, just to show you what the trajectory looks like, I create the time just from 0 to 1, 1 to 3 with 101 points. Then I compute what theta 1 and theta 2 is. Here is written as q1 and q2. You can see it's a function of time, in fact, a third order polynomial with those constants. I take the derivative of q1 and q2, which is shown here. And then I also do this step of computing the second derivative, because I want to see how the second derivative would look like. So I'm going to run this code. It's going to make a plots of several things: position as a function of time, velocity as a function of time, the middle panel, and acceleration as a function of time. The red indicates the second part of the trajectory. The blue indicates the first part of the trajectory. You can see that q0 is 0, q at 3 is 1, and in between there is I think we wanted 0.5, and that's what it is. If you look at the velocity, you can see the velocity is continuous. Here at t equals 1, velocity should have been 0.2, and that's what it seems like. So it satisfies that. Now, I did not enforce any conditions on acceleration. Okay, so what you see is that, as expected, the acceleration starts from 0, or shoots up to 2. Not good for the motors. It goes down -2, then shoots back down to, I think, very close to 0, and then it's slightly negative, and then shoots back to 0. But this is not good for your motors or the system which is providing the trajectory, right? So that's something to remember. Now, of course, I can take care of this by enforcing additional constraints on the acceleration, which I've not done here. For the next problem, we'll do that. Find a time-based parameterization for a revolute joint. So again, theta. The joint should move from 0 to 0.5, from t to 0, 1. So nothing has changed from the previous question here. 0.5 to 1, from 1 to 3, which is the same thing as before. Velocity of the joint should be 0 at the start, should be 0, and n should be 0. So that's all these things are the same for the previous question. What has changed is this statement. The acceleration of the joint at the intermediate point should be continuous. Okay, and assume two minimal order polynomials. Okay, so let's do this. I'm just going to set up the equation. So what we need here is two curves. Theta 1 of t and theta 2 of t. This is theta as a function of time. Okay, so let's impose all the conditions we have here. Okay, so condition on t equals 0 is it should be 0. Theta 1 at t equals 1 should be 0.5. Theta 1 at the start should be 0. Conditions on theta 2 are theta 2 at t equals 1 should be 0.5. Theta 2 at t equals 3, 1 should go to 1 radian. Theta 2 dot at the final time should be, so final time is 3, should be 0. Okay, so I've got these, I've got these, I've got this. Okay, and then last condition, acceleration of the joint at the intermediate point should be continuous, which means that theta 1 double dot at t equals 1 should be equal to theta 1 or theta 2 double dot at t equals 1. So that is the acceleration condition. Okay. Now, if you want to have the acceleration to be continuous, you also need to ensure the velocity is continuous. So theta 1 dot at t equals 1 should be theta 1 dot equals at t equals 1. So this is continuous acceleration and continuous velocity. Okay, so what we have here is three conditions, two conditions. So we have 8 conditions. So 8 conditions. So that would be 4 for theta 1, 4 for theta 2, which means that we have to do the same thing as before. We need to assume a third order polynomial for theta 1. So let's do that. And a third order polynomial for theta 2. We write this as theta 1 of t. This is theta 2 of t. So a20 plus a21t plus a22t square plus a23t cube. Okay, so I don't want to go to the process of setting up AA equals B here, but I would like you to do that yourself. I will give you A, it's in the code. So I did this whole thing, computed A, uppercase A, lowercase b, and then computed lowercase a by solving the equation in Python. And then I'm going to show you the plots, just like I showed you the plots for the previous one. Okay, so try to do that yourself and see if you get the same A as I got in my notes. So this is example 2. Here's the A, capital A or uppercase A, lowercase b. Everything else is the same. It's just copy paste. Just the A matrix and the B matrix would be different. So running this, he gives me a plot like this. So you can see the position looks very similar to previous case. Velocity is interesting. It goes from 0 all the way 0, but here it is continuous. Okay. Last time it was set to 0.2, so it was a bump and another bump. But here the acceleration is interesting. As you can see that it's actually continuous at t equals 1, and that was one of the conditions we imposed. But it's not continuous at t equals 0 and t equals 3. In order to do that, what you'll do is you'll put 2 more conditions on acceleration. You'll say that acceleration at 0 and 3 is 0, which means that you'll add from 8 conditions, you'll go to 10 conditions, which means that you'll have to have a 4th order polynomial for theta 1 and theta 2. Okay,